In this lesson, we are going to talk again about the sample autocorrelation function, which is also known as the correlogram for a time series. We will focus on the interpretation and conditions under which it makes sense to interpret. In this lesson, then, we are going to interpret carefully the output that is produced by the ACF function in R. And we are going to indicate the calculations that R is doing in the background using the sample autocorrelation coefficient R sub k formula. Interpreting the sample autocorrelation function requires that we introduce the role it plays in a statistical inference about the ensemble population's autocorrelation coefficient parameter rho sub k. So we do that introduction. And we see then that the interpretation of the sample autocorrelation function as an estimate of the ensemble's autocorrelation function makes sense only if the time series is stationary, meaning that it has mean invariance that does not change over time much. That is, a time series that has no trend, no seasonal component, and no change in variability is the only time series for which the interpretation as an estimator of the autocorrelation coefficient in the sample makes sense. Now, we are going to be saying all these statistical inference interpretation and these conditions of stationarity in a rather informal sense. There will be another lesson dedicated to the theory of stationary processes later on. Why is it important to know and mention all that? Well, the sample autocorrelation function, as we have already indicated, gives us all the values of the sample autocorrelations at different lags, R sub k's, and it's the most important statistic of a time series. So it's nice to see that statistically speaking, it is estimating the ensemble population ACF and helping us assess whether the true population correlation coefficients are zero. But, you know, as in all statistical inference problems, assumptions are very important. And so it's important to know that when applied to time series with trend, seasonality, or change in variability, the interpretation of the sample ACF as a statistical estimator is not the proper interpretation to make. So let's focus now again on the data set that we created in the previous two lessons. And you have it here in the middle. It's the Johnson-Johnson data set. JJ is the actual Johnson-Johnson time series, quarterly time series. And remember that we lagged the values of the time series and created new time series that contain the lagged values. This is the same data set that we used there. Okay, we use the notation that we introduced earlier. Y sub t will be the Johnson-Johnson itself. Y sub t minus 1 is the Johnson-Johnson lagged 1 quarter, and the YT minus 2, Johnson-Johnson lagged 2 quarters, and so on. And on the right-hand side, you have the formula for the autocorrelation coefficient in the sample that we had already also introduced in a previous lesson. And we said in that lesson that this autocorrelation coefficient formula, the autocorrelation of lag k, is different from the Pearson autocorrelation coefficient because of the way we represent the time series data, which is lagged value of the original time series. And the denominator is also different. And on the left-hand side, you have what we see when we run the ACF function and extract from it the coefficients, the little r sub k's that R has calculated. So the right-hand side contains things that we don't see in as we are running, right? How the calculations are being done by R. On the left-hand side is what we see. So let's focus now on the actual values of the correlation. So look at the 1. Well, 1 is the value that is represented in the autocorrelation coefficient by the first vertical bar. So the height of this first vertical bar is always 1. If you run packages in R, they remove it. Many packages remove this first one. Base R, which is the function ACF, is in base R, does not remove it. It's always going to show. So we call that R sub 0. If you look at the coefficient, how R is calculating that R sub 0 is just putting K equals 0 here. So the numerator is the summation from T equal 1 to N. And it reduces to the same summation that we are doing in the denominator, because Y sub T minus 0 is Y sub T. So you have Y sub T minus Y bar times Y sub T minus Y bar. So it's sum of Y sub T minus Y bar squared, which is the same as the denominator. And that's why the R sub 0, when K is to substitute for K equals 0, gives you 1. And that shows up in this bar here. And what that is just the correlation of YT with itself. So it makes sense that the correlation of a time series with itself equals 1. We can go and focus now on the second number, the second autocorrelation, the second R sub 1. This will be R sub 1. So that would be the sum from T equal 2 to N of YT minus Y bar times Y sub T minus 1 minus Y bar. So the number that you have, 0.9251, is the height of the second vertical bar in the sample autocorrelation plot. And that is the correlation calculated between these two time series. Notice how we start calculating R actually. So this is what we don't see R doing, but that's what R is doing. R is calculating the correlation between YT column and the YT minus 1 column. Let's look at another one, R sub 2. R sub 2, the third number in the output for autocorrelations, is usually R sub 2. That corresponds to the height of this third vertical bar in the sample autocorrelation plot. In the background, R is calculating the correlation between the column YT minus 2 using the formula for the R sub K that we have here on the right. So that's the sum on the top from T equals 2 plus 1, 3. Notice how we start calculating at observation 3, okay? And we ignore the others because they have missing values, okay? So it's the sum from YT minus Y bar times YT minus 2 minus Y bar, okay? So the correlation between these two time series. And we can do quickly the third one, autocorrelation at lag 3. So that will be the little R sub 3. It corresponds to the height of the fourth bar in this sample autocorrelation plot. In the background, without us seeing it, R is calculating using this coefficient R sub 3. R sub 3 is the sum from T equal 4 to N of YT minus Y bar times Y sub T minus 3. These two columns, the column for YT and YT minus 3. Okay, multiplied, and then you sum them up, sum the products, and so on. And then the denominator is just the sum of the first column minus the Y bar, this sample mean of the Y, for the whole data set. Remember that we are just showing the first observations, but this data set is much bigger, so it's nice that R is doing it for us in the background. We really don't see it. We just see the output. And for the last one that at least the last one that we calculated, R sub 4, right, is the height of the fifth bar. Here, the height of the fifth bar is 0.824. And that's the correlation between this YT column and the YT minus 4. Notice how now we start at observation 5. So the R in the background is calculating the little R sub K, R sub 5 equals the sum from T equals 6 to N. I'm sorry, 5. We are R sub 4. I'm sorry, we're calculating R sub 4 because it's like 4. K equals 4. R sub 4 equals the sum from T equal 5 to N. YT minus Y bar times Y sub T minus 4. This is the correlation between these two columns of the times of the data set that we put together. Okay, so that's the interpretation. And the question that comes next is, well, what are these blue bars that we get when we produce a sample autocorrelation plot with R? And remember, the sample autocorrelation plot, the height of these bars are the values of these coefficients at the least different lags K. And remember that the numbers in the bottom represent the first number is 1 year, and within 1 year we have 4 quarters, so there are 4 autocorrelations within a year. That's the interpretation. So what are these bars that we have here? Well, that is going to be the value of 2 standard errors. But 2 standard errors of what? Well, 2 standard errors of the little r sub k. So what is the standard errors? We will have to know what the standard error formula is. And why standard errors? Well, that brings us to having to think about a statistical inference. So before we get there, what we do is the following. If we have a bar that is outside these 2 standard error bars, we say that the autocorrelation at that lag k is statistically significant. And if we are inside the bar, if the autocorrelation, the heights of these bars, which represent r sub k's, is inside the bar, then we say that the r sub k inside those bars are not statistically significant. So here, for example, we have that R25, R sub 24, R sub 23, R sub 22 are not statistically significant. R sub 21 is borderline. All the other ones are statistically significant. That doesn't apply to R sub 0. R sub 0 is always 1. So, okay, so talking about statistical significance puts us in the realm of statistical inference. That's where we only studies in mathematical statistics and statistics, right? But inference for what? So that makes us think, well, if our little r sub k, the sample autocorrelation coefficient, has a standard error, that means that it's an estimator, right? It's an estimator for what? It's an estimator for the rho sub k. For rho sub k is just the parameter that is being estimated by this sample autocorrelation r sub k. And this parameter is the correlation, the autocorrelation in the ensemble. So the little r sub k is the estimator of the parameter rho sub k. So let's call this y, because that's how we've been calling our, and this is the mu, the parameter mean, the mean of y, okay? And let's call, and we also use x sub t minus k, not x sub t plus k, and we call it, let's keep calling it y and minus sign here, okay? So this estimator, little r sub k, estimates the ensemble, the population ensemble autocorrelation function. Okay, so the sample autocorrelation function is really an estimate of the population autocorrelation function. And in the population, we denote these things as parameters. Okay, and in the sample, we call them summary statistics. Okay, so that's the usual language in statistical inference. So this is the sample autocorrelation coefficient, and the rho sub k is the population. The rho sub k at every lag k, for k equals 1 to etc., is the population autocorrelation coefficient. So what is the hypothesis test that is being done when we use these 2 bars to determine statistical significance or not? Well, the statistical significance hypothesis test that we're doing is the following. We have the null hypothesis that the autocorrelation coefficient in the population is 0, against the alternative hypothesis that the autocorrelation coefficient in the ensemble population is different from 0 for all k. Okay, so we are assuming that the time series, right? There is no autocorrelation in the time series. So we just said that if the sample statistic, right, the little r sub k is outside the 2 standard error bars, we will reject that null hypothesis. We will say that the sample autocorrelation is statistically significant, means is significantly different from 0. We are rejecting the null hypothesis. So we use the summary statistic, like in every hypothesis testing, we have a summary statistic to do the hypothesis test. Then we have, because the summary statistic is a random variable, right? We have a standard error for the summary statistic, and this is the formula used for the standard error. And then we have a test statistic, and it happens to be a t-test statistic if we assume that the stochastic process generating the data has normal random terms, right? And so the t-statistic will be the r sub k minus the null. Usually is the summary statistic minus the null divided by the standard error of the statistic. That's a typical t-test, right? And so we have estimator, we have the standard error of the estimator, and we have a test statistic, right? So the test that we are conducting, which is rho sub k equals 0 against rho sub k different from 0, is done with the summary statistic f sub k. If r sub k is outside two standard errors, outside two standard errors really, if the t statistic is 2 greater than 2, right, then we have that the autocorrelation of is statistically significant, means it's giving us indication that the population rho sub k is different from 0. That's the interpretation. So what is the decision rule then? I'll repeat again. If the t is larger than 2, we reject the null hypothesis, or the same. The vertical bars in the sample ACF are outside the horizontal two standard error bars, then we reject the null hypothesis. Okay, but remember that when we do its hypothesis test, there is always a 5% at the 5% level of significance that are statistically significant just by chance. I mean, they are significant just by chance. They're not really autocorrelations. So there will be always some autocorrelations that are fictitious there, 5% of them. But we'll insist more on that when we start really using this in practice. So does this test work for all time series? Not really. The interpretation of the test only works if the time series have no long-term trends or seasonality. So the interpretation really does not work for the Johnson-Johnson data set that we have, because our data set, the ACF that we produce, is for the data with the trend and seasonality. When is the interpretation appropriate then? Well, it's appropriate if the time series is what we call stationary. That's a time series term. It's a rather abstract term, and we'll talk more about it in a future lesson. Simpler terms, that means that it means that the time series has no trend, has no seasonality, has no change in variability. In other words, it applies to the random component of a time series. Remember the decomposition that we did of time series into trend, seasonal, and random terms. Random terms is usually the component to which it makes sense to apply the sample autocorrelation to estimate the ensemble autocorrelation. So thus, we should use the sample ACF only when the time series does not have trends or seasonality and does not change in variability over time. In other words, use it only with the random components, okay? So a random component of a time series that has no increasing or decreasing variability over time is the perfect time series to apply the SAF to, okay, the sample autocorrelation function to. A series like that is called stationary. But again, we are saying this in a very informal way, okay? So what we notice in this lesson is that understanding what output R gives us when we use the ACF function and extract with ACF, $ACF, the autocorrelation coefficients R sub k. Excuse me, that takes practice, but we figure out what that is, okay? So the sample autocorrelation function plot produced by R has the two standard errors bar in it, And that requires a statistical inference interpretation of what we are observing in the sample ACF. So we went over the statistical hypothesis test that under the right assumptions is being done when putting the two standard error bars in the sample ACF plot. But we also discussed that the statistical significance interpretation only makes sense when the data has been made stationary or has constant mean, constant variance, no trends, no seasonality. In other words, it's a random term. So although we can calculate the autocorrelations for anything, for any time series, like we did for the Johnson-Johnson data, not only we do not extract much information that is not known from a time series that has a trend, but we cannot interpret the results as a statistical inference results because the assumption of stationarity does not hold. So I hope you enjoyed this rather a little theoretical presentation, but focus more on the interpretation and how to extract the values of the autocorrelation. And in future lessons, we are going to learn about how the sample autocorrelation functions of different stochastic processes will look like and can become more familiar with their interpretation. So I will stop sharing now.